You may know how to calculate pressure and density altitude and can use tools like our pressure and density altitude calculator linked here on the Flight Insight website, but do you understand what the concepts mean and how they apply to flight planning? At Flight Insight, we've seen that a consistent weak area on private pilot check rides, and other check rides for that matter, is an understanding of pressure and density altitude, how to calculate it, and what it means for aircraft performance. Let's review. Air has mass. It doesn't feel heavy, but all the little air molecules you fly through have mass. If we take a parcel or a space of air, it'll have some of these air molecules in it. On a day with low pressure, the air molecules are spaced out and diffuse. On a day with high pressure, they're packed tightly together. The airplane loves high-density air. The propeller produces more thrust in higher density air. There's more air molecules for the blade to push. The wing generates more lift in higher density air. There are more air molecules for the wing to turn and deflect downwards, and the engine produces more power. Engines, just like a campfire, require air to breathe and combust, so more air in the cylinder means more power produced. So we care about the density of the air, and we want a way to express it in a way that helps us with flight planning. Air density is affected by a few things. When we're flying, there's an ocean of air above us, in a column going straight up to space. The air molecules in this column compress the ones underneath so that close to the surface, all the molecules above contribute to a certain air density, while at a higher altitude, fewer molecules above contribute to a lower density. So airplane performance is poorer at higher altitudes. Temperature affects air density. Cold air has less energy and the molecules don't move around much, so group together. As air temperature increases, molecules start moving around and bouncing off each other, spreading out and making the air less dense. Aircraft performance is poorer in hotter temperatures. Weather affects air density. A high pressure system brings cool air from up high and pulls it down toward the surface, compacting air down there. A low pressure system sucks air from the surface upwards, leaving the surface with lower density. Aircraft performance is poorer in a lower atmospheric pressure. Water vapor in the air, or air humidity, also plays a role in performance. More humid air is less dense and worse for performance, but we're going to ignore that in the discussion of pressure and density altitude. So let's look at altitude on a vertical scale. We've got 3 frames of reference to help us out. The first is here in Maryland, close to sea level. The second is Kansas City, in the middle part of the country where the elevation is a bit higher, 1,000 feet. And the third is Denver, the mile-high city at about 5,000 feet. We already know that aircraft will perform differently at all 3 locations because of the altitude differences. Our aircraft is at 5,000 feet MSL. That's true altitude. It would be great to be able to say, my aircraft will perform the way it does in Denver, also at 5,000 feet, but we know there are other things that affect performance besides just our true altitude. Air pressure is one big thing that affects performance. Because air pressure changes day to day, we can't just say our aircraft at 5,000 feet true altitude will perform as if it's in Denver. But we can say, if there's a fantasy land where air pressure is always the same, our aircraft will perform like it's in Denver. In this fantasy land, which is really called the International Standard Atmosphere, sea level pressure is 29.92 inches of mercury, and the lapse rate is about 1 inch for every 1,000 feet of altitude gained. If these conditions held, we could say that our aircraft at 5,000 feet true altitude will perform as if it's in Denver, and the way we say this is that our aircraft is at 5,000 feet pressure altitude. The official definition of pressure altitude is our height above the standard datum plane, 2992 at sea level. Of course, we're not in fantasy land or the standard datum plane. If the actual sea level pressure is lower, the aircraft will perform worse. So instead of a pressure altitude of 5,000, maybe it's now 8,000. Our aircraft will perform as if it were at 8,000 feet in Fantasyland. And of course, air pressure isn't the only factor in performance. Temperature matters too, and our Fantasyland is always the same temperature. 15 degrees Celsius at the surface, getting 2 degrees colder with every 1,000 feet gained. If the temperature is different than Fantasyland, say it's warmer, our aircraft performs even worse. Now, instead of saying it'll perform as if it's at 8,000 feet, we may say it'll perform as if it's at 9,000 feet. This is called density altitude, which was pressure altitude, which we took and corrected for non-standard temperature. If I take a true altitude, a sea level pressure, and a temperature, I should be able to say what my aircraft would perform like if it were in Fantasyland, experiencing the same air density, and that's what density altitude is. Let's look at an example. If we're at an airport in Maryland, a true altitude of 100 feet, with sea level pressure of 30.22 and a temperature of 25 degrees Celsius, what's our pressure and density altitude? Let's start with pressure altitude. We take our true altitude of 100, and we're going to take the difference of the standard 2992 and the reported pressure of 3022. Our aircraft will perform the way it would in Fantasyland in Kansas City. That's what density altitude tells us. Notice also that temperature has a much larger effect on performance than pressure. 30.22 and 25 degrees are perfectly normal conditions and aren't too far off standard, yet the pressure altitude only changed by 300 feet, while the density altitude swing caused by temp was more than 1,000. Check out a few more examples of these on your own to get comfortable with it, and as always, check out all our Flight Insight ground schools and more at the website linked here or in the description. See you there.